Okay, this is day 3 of Unit 1. Today we started with this warm-up, and I'm actually going to go over number 2 first here. So let's go ahead and get started, and then we'll go back to number 1 in just a moment. So your school is sponsoring a charity race. Which subset of real numbers best describes the number of people, P, who participate in the race? So we discussed in class yesterday all of the different types of subsets of real numbers. And so with this, if you're thinking about how different numbers of people could participate in the race, well, they can't have decimals or fractions. And so whole numbers would be an option here, or possibly natural numbers, depending on your kind of thinking about this. If you're thinking that at least one person has to show up for a race to happen, then you would say the natural numbers. And if you're thinking that the race is still happening that day, it's just no one shows up, so 0 would be possible, then you're saying whole numbers. So I would accept either whole or natural here, depending on your argument, depending on your thinking. Either would be fine. All right, then we talked about just this real quick warm-up here, the review of simplifying radicals, because that's what our lesson is about today. And so just a reminder for how to do these. These are all problems that you should already know how to do. Square root of 16, well, that's a perfect square, and it's just the square root, which means it's the principal root, meaning I'm not thinking about positives or negatives here. It's just simply the square root. And if you're not sure what I mean by that, if you thought the answer should be positive or negative 4, which it's not, it's just 4. But if you thought plus or minus, then you're getting a little bit confused what a square root is. Grab a calculator, type in the square root of 16. 4 is the answer. Okay, and you're thinking of something else if you're thinking plus or minus, which we will discuss later in the year. The next one, the square root of 75. So I want the perfect square, which is 25, and then 25 times 3. So square root of 25, square root of 3 simplifies to 5 square root of 3. Again, this was just a real quick review from what you already knew in Algebra 1. Next, cube root of 27. So similar to how you approached these first two with square roots up, except that now we're looking at numbers that we cube. So 27, like 16 was a perfect square, 27 actually is a perfect cube. The cube root of 27 is just 3. Some of you, I'm sure, got that without any work. If you needed any work, what you're thinking is 27 is 3 cubed. So if I take the cubed root of 3 cubed, the cube root undoes the cubing, so that just means 3. And same thing here with back to B. If you were able to get 5 root 3 just in your head without showing work, that's fine. I was just showing kind of the process, the thinking process there. All right, so that was the warm-up. So then we went ahead and got started here with some examples. Again, we're going to be taking simplifying radicals just a little bit further here today than what you probably did in Algebra 1. So let's get these two copied into your notes. So the first one here, this one's not quite like the cube root of 27 because 24 is not a perfect cube. There's not a number I can cube to get exactly 24. So what I do have to do is kind of similar to how we approached the square root of 75 in the warm-up. I need to think of a perfect cube that goes into 24. And some of you, I'm sure, just thinking about it, know that perfect cube. Others may not know what perfect cube goes into 24. So if you're in the boat where you don't know what the perfect cube is, then what you'll do instead is you'll start with 24 and you'll make a factor tree. Basically, we're looking for the prime factorization. All of what I'm saying here should sound familiar from Algebra 1. So any two factors of 24 you can start with. I'm just going to do 6 and 4. You could do 2 and 12 or so forth. Then I'm continuing to factor until I get to the primes. So I have 2 times 3 and 2 times 2. Now I have the prime factorization of 24. So I'm remembering that the prime factorization of 24 is 2 times 2 times 2, which is 2 cubed, times 3. Now back over here, I'm looking at finding the cubed root of 2 cubed times 3. Well, the cubed root of 2 cubed, remember, like we did in the warm-up, we're undoing cubing by cube rooting, so that's just 2. and then I'm left with the cubed root of 3, and I can't simplify that any further. So 2 times the cubed root of 3 is my final answer. Now, if back to how I started this, I said if you're able to figure out what the perfect cube is, well, the perfect cube that goes into 24 is 8. So 8 is 2 cubed. So it could have gotten there a little bit quicker if you just knew that this was the cubed root of 8 times 3. That's cubed root. Then you would get to this step here and then this final answer without having to do the prime factorization and the factor tree. Either way is fine, whether you need the tree or not is fine. So similar approach on this one. Now that I kind of know how to do the quicker way, I do realize that 8 is a factor of 40, and we now know, if we didn't before, that 8 is a perfect cube, 2 times 2 times 2. So I'm going to just start right here in this step here, not do the tree. Again, if you'd like to do the tree, that's fine, but I'm going to take the cubed root of 2 cubed, because that's 8, and 8 times 5 is 40, so the cubed root of 2 cubed times 5. Well, the cubed root of 2 cubed is 2, and then I'm left with the cubed root of 5, which does not simplify any further. Continuing on. All right, so then I had students write this rule, which this you learned in Algebra 1. I'm just simply reviewing it. So just write that in your notes. And then after you have that written down, we are going to take a look at using that rule with each one of these examples. So what the rule says, first of all, not even looking at the root yet, but just following the rule and putting the correct numbers in the right spot. It says I'm supposed to put the a, which is the exponent here when it's in radical form, as the numerator of the exponential fraction, and b, which is the root in the radical form, I'm putting that in the denominator. So I'm going to do that, but also I am going to pay attention to what type of number the root is, which, by the way, we call that number in the b spot, the root, we call that the index. Okay, so whatever the index is, I am going to take a look at that. And if it's an odd number, I'm just going to follow this rule, and that's it. I don't have to do anything else. In a minute, we'll talk about what happens if that index or that root is an even number. There's a little bit more work to do there. But this is an odd root. The index is 3, so I am going to just go ahead and apply the rule, which says I'm going to rewrite this as x to the 12th divided by 3 power. Well, 12 does divide by 3 evenly, so we're going to do that, and we're going to get x to the 4th as our answer. Similarly, again, the index is 3, and so I'm supposed to just apply this rule, so that would give me x to the 2/3 power. Now, what I told students in class, though, is technically I did what I was supposed to. I followed that rule, and I rewrote it as x to the 2/3, but technically I didn't really make this any more simplified. It's important that you know both forms, that you know radical form, and that you know exponential form, the fractional exponent, that you know that these two are equal. But x to the 2/3 is not any more simplified than the cubed root of x squared. So if you want to just leave your answer as the original problem, the cubed root of x squared, that is fine. And again, because it's not really considered any more simplified to put it in fractional exponent form. That's different than the last one, because x to the 4th is considered more simplified than the original, the cubed root of x to the 12th. So it is important that we follow that rule there. But on this one, because the numerator of the fraction is, the number is smaller than the denominator, then I'm actually not able really to do anything else with that. And so that's why I'm saying it probably is best to just leave it in its radical form. Next one. So I am going to rewrite this as x to the 5/3, right? Again, following that rule, but 5 doesn't divide by 3 evenly. So now are you saying, well, is this going to be like this last one where I'm just going to keep it in its original form? Well, not quite, because this time the numerator is larger than the denominator. And so even though 5 doesn't divide by 3 evenly, it does divide by 3. So we do want to do a little bit more work with this one. So when that happens, when your numerator number is larger than the denominator, what you'll do is we'll go back to the original form, and we're going to just rewrite this we're going to break down x to the 5th into smaller pieces. And so what we want to do is, remember, we're trying to divide by 3, and we're trying to do that evenly. So the next smallest number from 5, if I start at 5 and I'm going down, can't go up, but I can go down, the next smallest number that does divide by 3 evenly would be 3. So I'm going to rewrite x to the 5th as x cubed. And I can't just change the problem. I still need the additional x squared that is being multiplied. And by the way, I am correct here. You should be thinking back to your rule. X to the 5th is x cubed times x squared. So I haven't changed the value of the problem. It just looks a little different. But x cubed times x squared is x to the 5th. So I'm good. And again, the reason I'm doing that is because it's easy for me then to take the cubed root of x cubed. So that's what I'm going to do. After rewriting, I am going to take the cubed root of x cubed, and I'm going to get x. And then I'm left with the cubed root of x squared. So I have x times the cubed root of x squared is my final answer. Okay, and that is considered the simplified form of the original radical. All right, so one more. This one's similar to the last one, because if I rewrite this as a fractional exponent, I would get x to the 12/5 power. And I can write that, but you don't even really have to write that, because we are going to break it down into pieces like we did the last one. So remember, I'm trying to divide by 5 evenly, and that would mean that I need x to the 10th, because 10 does divide by 5 evenly. Now, it was 12, and I wrote 10, so that means I need x squared to be multiplied by that x to the 10th to be equal to the original. So now I'm able to divide. Remember, if I'm writing this as a fractional exponent, it's going to be the 10/5 power, and 10 divided by 5 is 2. So I'm getting x squared on the outside of the radical. I still the 5th root, and then I'm left with that x squared, which I can't simplify any further because 2 is smaller than 5. So my final answer is x squared times the 5th root of x squared. Moving right along. So you just wrote in your notes the rule to follow when the root or the index is odd. Now we're going to take a look at when it's even. So we'll do the same thing. Notice the a and the b are still in the same spot. A is the numerator, b is the denominator, but now we have that expression inside of an absolute value. And you might be saying, well, why do we have to do that for evens? Well, think about it. We talked a little bit yesterday when we wrote our chart and with the subsets. We talked a little bit about imaginary numbers, and remember, we talked about the fact that anytime you have, I gave an example, like the square root of -2, well, that's going to be an imaginary number. Well, we're talking about real numbers here for this, for simplifying radicals. So if this was an even root, like a square root or a 4th root of a negative number, then we would be dealing with imaginary numbers, which we don't want. So that's why we have to then take this expression, following that rule, and put it inside of an absolute value, because we want to avoid those imaginary numbers. Now, we don't have to worry about that if it's odd, because I can take the cubed root of a negative number, like the cubed root of -125, let's say. Well, that's -5, because -5 times -5 times -5 is -125. So that's why it only applies to when the root is an even number. Okay, so anyway, we are going to apply that rule like we've been doing, but then we're going to put the expression inside of an absolute value. So, first of all, there's no index here. You learned way back when that when there's no number written there, it's a 2. I'm going to just write it, even though you already know that. I'm going to write it to make things easier on myself. Same thing on this next example. I'm going to put the 2 there. So then we're going to apply this rule, and that says we're going to divide 6 by 2, and we're going to get 3. So we're getting x cubed. But then, because this root was even, 2 is an even number, I have to put that inside of an absolute value. And my final answer is the absolute value of x cubed. All right, we're going to do the same thing on this next one. So first of all, I am going to use this rule. I'll worry about the absolute value in the very end. But for right now, I'm dividing 3 by 2. I can't do that evenly, so we'll do like we did on those last examples. We're going to break down that x cubed into x squared times x. And again, that's right. This is a first power and the second power add to 3, so I'm good. Square root of x squared is x, and I'm left with the square root of x. Again, I'll worry about absolute value in just a second here. I'm going to do the same thing with the y's, so I am going to see if y to the 8, if I can divide that evenly. I can, so 8 divided by 2 is 4, so I'm just getting y to the 4th. And lastly, z, this is z to the first, and that number 1 is smaller than 2, so that z is going to stay where it is. So let me just throw this y to the 4th in front of that x, and let me just put this z underneath. And now I'm going to go ahead and take that whole entire expression, which is my answer, and put that inside of an absolute value. Okay, why did I do that? Because the root is even. Okay, now, this answer is okay, but it's actually technically not quite correct, and we're going to talk about why right now. So I want you to think about expressions that need to be inside of an absolute value. Now, first of all, this piece right here, the square root, we've already indicated that it needs to be positive, and it'll always be positive when we're dealing with real numbers. So whatever you have underneath the square root, that doesn't need to stay underneath or inside the absolute value. So I'm going to go ahead and pull that out. I don't need that inside the absolute value. I followed the rule and said just put everything in initially, but now I'm deciding what actually has to stay inside the absolute value and what doesn't. So I'm left with this x and this y to the 4th, and I'm deciding if they both need to stay inside the absolute value or if the absolute value is actually irrelevant. So let's think of some numbers here for x for just a second. So let's just try some positives and negatives and see what makes a difference here. So let's say x is 2. Well, the absolute value of 2 is 2, so that didn't change anything. Now, let's say that x was a negative number. So inside of that absolute value, the absolute value of, let's say, negative 2 is 2. Being inside of the absolute value changed the value because it was absolute value of negative 2. So the x has to stay there because it is changing when the value of x was negative. With the y to the 4th, again, we'll just use 2 and negative 2. So 2 to the 4th is 16. The absolute value of 16 is 16. So that didn't change anything. Now, negative 2 to the 4th. Well, negative 2 to the 4th is also 16. So it's still a positive. And the absolute value of 16 is 16. So did putting y to the 4th inside of the absolute value change the value? Well, no, because an even power, whether the original number y was positive or negative, didn't make a difference because a positive or a negative number taken to an even power will always result in a positive output. So even though I initially put the y to the 4th inside of the absolute value, because that's what the rule told me, I'm realizing it's actually unnecessary to be inside of the absolute value because anything to the 4th power will always be positive. It doesn't have to be inside of the absolute value for me to know that. It'll just always automatically be positive when we take a number to an even power. So what I'm going to do is I'm actually going to take that y to the 4th out of the absolute value. I'm just going to stick it here in the front, and I'm going to only keep that x inside of the absolute value. So let me do that, and then again, I'll explain why we did that. I have a y to the 4th not inside the absolute value. I have an absolute value of x, and then I have my square root of xz. Again, that doesn't need to be inside. That is my final answer. Okay, so let's make sure we get this straight so you know when you need absolute value and when you do not. So first of all, you're looking at the root, and when the root is odd, you will never need an absolute value. So those are the easy ones. You don't have to worry about absolute value at all. When the root is an even number, you will need an absolute value around your expression. Again, I put it around the whole thing initially, but technically speaking, the only part of your answer that will require an absolute value in the end result is when we have an odd exponent. So this is x to the 1st power, 1 is odd. that needs to keep the absolute value around it. Nothing else actually needs an absolute value. Even powers don't, and square roots don't. Just when the original was an even root and the exponent of the final answer is an odd number. Again, this is a 1. That needs an absolute value around it. Nothing else needs an absolute value. All right, let's look at a couple more examples and then be done for today. So I'm going to take cube root. Both of these are cube roots. So again, 3 is odd. I'm not going to worry about absolute value on these. What I am going to do is think about what the cube root of 32 is. I'm not really sure about this one, so I'm going to do a factor tree off to the side. 8 times 4 is 32. 4 times 2 is 8. 2 times 2 is 4, and 2 times 2 is 4 again. So we're getting 2 times 2 times 2 times 2 times 2. 2 to the 5th power is 32. Okay, but we want to break that down into cubes, so we want 2 cubed times 2 squared, right? 3 plus 2 is 5. So I'm taking the cubed root of 2 cubed times 2 squared, and when I take the cubed root of 2 cubed, I'm getting 2, and I'm left with the cubed root of, whoops, that should be squared, and I'm left with 2 squared, which is just 4. So I have 2 times the cubed root of 4 for the number part of my answer. Now I'm ready to do the same thing with the x to the 5th, break that down. Remember, I'm trying to break it down into numbers that evenly divide by 3. So I'm doing x cubed and times x squared. And 3 plus 2 does add to 5. So I'm able to take the cube root of x cubed and get x, and I'm left with the cubed root of x squared. Lastly, the y cubed, I'm breaking that down. Oh, actually, I don't need to break that down because 3 does divide by 3 evenly. So when I take the cubed root of y cubed, I'm simply just getting y. All right, remember we said no absolute value on this because no even root. This is odd. So I'm ready to put all of this together in my answer. I put the 2 first. Technically, we normally go in alphabetical order. So x, y, it doesn't have to be, but we usually do. Cube root, and then I have my 4x squared, and that is my final answer. All right, next, cubed root of 81. So I'm looking at the tree here. 9 times 9, 3 times 3, and again, I'm getting 3 to the 4th. I want cube root though, so I'm going to rewrite that as the cube root of 3 cubed times 3 is 3 to the 4th is 81. So cube root of 3 is 3, and I'm left with the cube root of 3. That's a lot of 3's. 3 cubed root of 3. I'm done with the number part. I'm ready for the variable part. I want to break down that 5 into things that divide evenly by 3. So that would be a cubed and a squared. 3 plus 2 is 5. I'm ready to take the cubed root of a cubed, which is a, and I'm left with the cubed root of a squared. Last piece, I'm dividing 12 by 3. It does divide evenly, so I'm just going ahead and doing that. 12 divided by 3 is 4. I'm getting b to the 4th. All right, I'm ready to put the expression together, all the pieces together. Remember, this is odd root, so no absolute value. The 3 and the a and the b to the 4th are all outside of the radical, so I'm going to write them first. And then I have my cube root of 3a squared, and that is my final answer. All right, we're going to take a look at 2 more for today. So these are both even roots. These are both square roots. I'm putting the 2 to help myself. I am going to worry about absolute value on these in my final answer. So I'm going to go ahead and first of all divide 14 and 4 both divide evenly by 2. So this one's actually not too bad. We are going to divide and get x to the 7th, and 4 divided by 2 is 2, so y squared. And now, and remember, initially you can put the whole entire expression inside of the absolute value, but really we're concerned about what needs to stay there. Odd exponents need to stay inside. Even exponents can go out. So y squared times the absolute value of x to the 7th is my final answer. Next, simplifying the square root of 18. Well, you're pretty good at simplifying square roots. You've been doing it for a long time, so that should be quick and easy. Square root of 9 times square root of 2, 3 square root 2. So that's the number piece. Next, we're dividing 4 by 2, and we're getting 2, so x squared. Next, 5 divided by 2 doesn't go in evenly, so I'm breaking down that square root, that y to the 5th into y to the 4th, because the 4 does divide evenly. And then I have y to the 1st power left. 4 plus 1 makes 5. So I'm taking 4 divided by 2, and I'm getting y squared. And I'm left with that square root of y. And lastly, the z's, 10 does divide by 2 evenly, and I'm getting z to the 5th. So I have this x squared, I have this 3 square root 2, I have y squared times square root of y, and I have this z to the 5th. And remember, initially, all of that is inside the absolute value because of it being an even root. Now I'm ready to determine what can go out of the absolute value and what has to stay in. Remember, it's an even root in the initial problem and odd exponent in the end. So that z to the 5th must stay. The y squared and the x squared and the number 3 and the square root of 2 and the square root of y, they all come out. So the only thing that's going to stay in is that absolute value of z to the 5th. So let me put the pieces that are in front first. So I have a 3. I have an x squared and a y squared. Now I'm ready for that absolute value next, and that would be absolute value of z to the 5th. And last, I'm ready for that square root, and we have a 2 and a y that are underneath that square root, and that is our final answer. And that is it for our lesson today. So you will follow your assignment for homework that is on the agenda in Schoology.